Okay, so this is a little bit older data, but this is coming very much from what we're talking about before, looking again at ternary blends. And this really comes down to our pavements. And I'm not going to dig on our transportation engineers, but I am going to make a little bit of dig on our transportation engineers. So I apologize to those of you in the audience. Certainly when we look at sustainable pavement design, it has to be economical. And certainly we're looking at how do we minimize materials, and we're looking at congestion and rehabilitation and so forth. And when we look at sustainable pavements, you know, there's a lot of things that we can look for in a pavement. Certainly we can look at reduced fuel consumption. These are the things that the Sustainability Hub here in Boston are looking at. They're looking at lighter, brighter colored pavements. Does that help with the albedo effect or the heat sinks that are happening in cities? Certainly it does. We're talking about new areas to grind and rehabilitate those. And certainly we've seen, other improved stormwater qualities with pervious concrete, but it really hasn't been adopted widely. I'm not going to dwell on this. We've looked at this in the previous presentation. But I really like to talk about when there's really 7 principles when we talk about sustainable construction. It's really reducing our virgin resource consumption, reusing recyclable resources, we're protecting nature, eliminating toxins, and we're seeing more of that now that we expect to see EDPs that actually ask you to quantify these. It's a focus on quality though. These pavements should be designed for longer than what they're designed for now. Certainly I come from an area and we always laugh because Bellefontaine, Ohio is known for the longest pavement in the United States. It's over 115 years old. It's concrete pavement. Well, they have rehabilitated it many, many times, but there's still sections that are original. But we have to really look at life cycle economics too. Today we're really tasked, and I know that this has been a big point here at convention. We're dealing with limestone cements. And those limestone cements have played a part in how we design. And certainly they have impacted the way I design, certainly. And we're producing more limestone cements now. Most of the data I show here was done with Portland limestone cement. It was done, though, almost 10 years ago, a decade ago, and this was primarily done for the Canadian market. But we wanted to extend it and see what those pavements would do in our own markets. And so we were looking at a limestone cement, type 1. Now, this was looking at a limestone cement that was produced over in Alpena, Michigan. Certainly, why they say the blend is increased to compensate for the lower clinker content, we're seeing that that blend today can cause a little bit of air issue, and there can be some quality issues as well when that blend is going up and down. So certainly you need to be aware now with the new pavements and the pavement specifications that are coming out, you need to have some consideration again for your materials. So with the consumption approaching, and the reason we've done this is certainly that as we see the consumption approaching to 20,000 million metric tons of concrete that's being produced annually, certainly we're concerned about the CO2 and the CO2 that's being produced. Certainly we can do, the main source of CO2 for those of you, I'm sure this is not new, is from CO2, but there are many, many levers that are used by both the industry, your producers, and the cement manufacturers. And certainly the way to do that is to make blends. And so blends, can be very useful, but you've always got to keep in the back of your mind, the amount of cement that's used in a mixture is only between 7 and 15%. And then some of that is also air content and other materials. A lot of that CO2 is reabsorbed into the concrete through carbonation. Now, there are not a lot of good studies right now that look at carbonation. The best is the Sweden study. But the materials you use will also impact that CO2 absorption. A lot of people want to bank on that statement. But when you start using SCMs, that reabsorption through carbonation is slowed at best. So some of the things that we've seen is the levers from the cement manufacturers is really to improve the efficiency of their assets, lower and use biofuels, certainly use blended cements, reduce clinker production. And the way they do this is basically by the removal of portions of the cement and by using the additions, whether it's blast furnace slag, silica fume, fly ash, natural pozzolan, so forth. That is what's added into the finished product. Now it can be blended, or as we know as producers, it can also be done at the plant. So certainly industrial byproducts are big into this, and we've talked about silica fume, fly ash, and certainly slag. But it reduces landfill disposal, obviously, but it does improve service life, is what I've shown in the last section. And certainly here are the most common SCMs, but if you come today to ACI, you see things more like volcanic tuffs. You're looking at bottom ashes. You're looking at other new materials, ground granulated glass. Things like that are coming into the marketplace. So you need to be aware what you have coming into your market, when it's going to come online, and certainly ask for that pozzolanic index. What is the activity of these types of materials? These are obviously well studied, which I have here, and more are coming. And certainly by looking at the energy savings, you can reduce this by, this is an older graph, thank you, Eckhart, he's left, but I borrowed this from him, where it shows like just the substitution, how much energy savings there are, and then also the reduction in CO2 in pounds. So the study that I looked at was looking more at binary blends and ternary blends, and certainly we saw a quad blend on the last presentation. And again, it's managing that particle size and making sure that we're densifying the concrete to our ability to make sure we can extend service lives. And certainly we can see that particle size is a big indicator of how you're going to change the permeability and the tortuosity of those concretes. Certainly most of us know how that pozzolanic reaction works, but for those of you that don't, certainly some of these are making additional glue. Then we have to have the hydroxide reaction, which activates some of our pozzolans. Slag cement is hydraulic in nature, and so it just add water and we'll get a little strength gain out of it. But certainly when we look at North America in comparison to what's going on around the world, we do not use a lot of blends. And certainly if we look at North America, you can see we're sorely behind in the use of blends. It's hard to get them adopted. People aren't used to using them. They prefer to use what they're straight Portland cement. But certainly by looking life cycle assessment, which I talked about earlier, we can really see, if we start going to blends, that we can reduce raw material acquisition. We can also reduce some of the manufacturing. Maintenance and disposal will go down as well. So maintenance costs are extremely reduced when you start having proper service life. And certainly when we look at the environmental performance, this is something that looks at just the difference between a Portland cement, 10% limestone at a 4,000 psi mix, and if we use 50% slag. So we can see there's a different environmental score. This is the BEES program, which isn't used much anymore. However, to do a proper EPD, we still don't have an EPD yet for silica fumes, so while it's coming, and fly ash doesn't have an EPD either, we don't have those figures yet for the reduction in CO2, but they're forthcoming shortly. And so also we can see the overall performance, that if we talk about the economic performance and the environmental performance, using things that have blended cements are actually much better than using a straight Portland cement. And so certainly I won't linger on this. We know that you can change the plastic and the hardening properties. This is an old slide, an oldie but a goodie, so we're all laughing at it. But then we look at the impact of service life and operating energy. And again, this is a slide that's not often seen, but really it's a good slide because it talks about if I have a material and I'm just using, it's a high operating cost because I'm going to have to maybe repair this structure over and over again. But if I don't have to repair it, I'm really limiting my energy over the course of time. And when we look at this as the materials are 15% of the total, but it's really this operations portion that is the bigger section, and that is your maintenance. That is your maintenance cycle over and over and over again. So the way I like to look at it is I live very close to a highway. They've replaced that highway 6 times with asphalt in less than 20 years. The concrete pavement that is close by on a similar highway, put down 20 years ago, has never been replaced. So which one has the higher operating and CO2 levels? It's certainly the asphalt in this particular case. So when we look at embodied energy, which is another name for CO2, we really have to look at the total impact of the structure. And again, this is where I come back to service life and durability. And so durability, for those of you that don't study it a lot, is really how is your structure reacting in place? What are its in-place exposure conditions? And certainly, you know, we have different exposure conditions here versus a bridge versus this was a ductile lightweight rail. And we have to take all of these into consideration. But the other thing that we don't really consider in a lot of ways is it can be a function of service of quality and service life. And really we have to look at the specified quality, the minimal acceptance quality, and then what happens when the structure fails over time. And the thing that's not well studied in our industry right now is the differential durability and how that plays a part in our structures. So what I mean about differential durability is if you have different components, what are their durabilities between those components? So why I can have a structure that is a building, I still have maybe caulk that I'm using. How often do you replace that caulk in comparison to you replace the concrete? I think where we need to go is we need to have closer levels of differential durability in some of our materials so that we can withstand some of these hazards and also have a better service life overall. And so they also require, when you have differential levels of durability, you have varying levels of maintenance, repair, and replacement. And this is what you have to keep in mind is even though you might have built a concrete structure, if you didn't use the proper mortar or you didn't use a proper type of finishing or, you know, you didn't seal it correctly, you could have many, many areas where you're just racking up CO2. And so it's the extent and the intensity of these kind of items when we're doing maintenance that we have to keep in mind for the overall amount of embodied energy in a building. So when we looked at sustainable ternary blends, it's really, in my opinion, Kevin touched on it too, is if you use just enough silica fume, you can really optimize your design. And this is what was the case that we were doing in something we were doing for the highways in Cleveland, Ohio, and these were really for approaches. So what we were looking at is looking at a mix that was typically done for these approaches. In our ODOT, our Ohio Department of Transportation, we have different JMFs, as he explained, job formulations. And so one that was popular was 658 pounds of Portland cement. So what we did is we looked at what would be the impact of changing by looking at a binary versus looking at a binary with silica fume, looking at a binary with slag cement only, and then looking at the combination of making it a ternary, which is using also the blend with 25% slag cement with 6% silica fume, 25% of slag cement with 4% silica fume, and then looking at these types of blends. So you can see that there is a reduction in Portland cement. Unfortunately, the calculators today don't calculate them very well with CO2 savings, but by just going to a 25% blend, it's about a 20% reduction in CO2. And I would believe the silica fume, if we could make this even a lesser cementitious mix by using the silica fume, it would probably even be further reduced. So here's what happened in the compressive strength. As we can see over the course of time, the Portland cement is about 6,800, but as we start adding and making these a better ternary blend with the same cementitious contents, you can see here at a blend of basically 4% with 40% slag, 4% silica fume, 40% slag cement, we're at almost 8,500 psi. And then again, 7,900 when we start to look at these blends. So where am I really getting the bang for the buck? And here's where we have to start looking economically. If I just had the Portland cement blend, it's fine, but I believe I would have to go back and really look at the durability issues on this, and we did, which is pretty much where I'm going with this, is that, oops, I went backwards, that when we looked at the service life of these particular blends, and we looked at them further, we could look at the limits and how they were going to prepare, how they were going to look. Well, we looked at ASR mitigation because obviously that is a big concern to us, and what the allowable limits were. So when you have a GU cement, it can somewhat be highly reactive when you have reactive aggregate. So a GU cement is just basically a type 1-2. But as I add the ternaries, I see I'm well below the maximum allowable limit. So this is going to use, when you start using blends, it really helps you when you have areas where you're concerned about ASR, or you may have other moderately aggressive soils or other aggregates that are reactive. So certainly when we did this study, we also looked at rapid chloride permeability. And we did not take this. This is, I don't know how many of you are familiar with this. This is why I put the test up here. You take a cylinder, you make a slice, and then you force the chlorides through it to see how fast they pass. And when we looked at the RCP data, it became really apparent to us where we were really finding our sweet spots. So the Portland cement is obviously quite high, and so when we look at chloride penetrability, or how fast the chlorides are going to penetrate, certainly we're very high here. And in Ohio, we salt our roads. We use some brine, we use salt, but obviously this is not going to be a very durable pavement. And so when we added 4% silica fume, it got better, and silica fume, we also saw that it was better, but now slag better. But when we actually got down to the blend, we were really seeing where we were going to see payback. Now what I want you to notice is that most RCP data only occurs at 20 days, 42 days. We actually looked at these at 2 years. So this is long-term data. And this is the best way you can actually get an M coefficient, so you can actually look at the true durability or the service life. And so we did see anomaly where it did creep up here, but that could have, to me, that's an anomaly because I would have expected it to be lower, so perhaps there was a hairline crack or something in this particular data set. But we looked at the models that we also used was the Stadium software model. This was where the apparent chloride diffusion coefficient was done. We looked at the diffusion cells. There was a grinding procedure. I'm not going to belabor this point. I think it's more important to look at the data when we look at the coefficients. So when we look at these coefficients, which is, this was a 658 again, this was a 0.43 water cement ratio. Air content was about 6.5% to 8% for these specimens. The slumps were all maintained between 5 and 7. We can see that the coefficients are going down. Now remember, this is an exponential scale here. As we go down, we can see at 2 years, look at the amazing amounts of reduction in permeability that we're receiving here. And so this is talking about 40% slag. It's done quite well. I was kind of surprised to see the blend a little higher here. 4 and 40, this is slag and silica fume. And again, the best blend, as I would expect after looking at long-term data, is what we expected was the 6% silica fume with 40% slag cement. So even we can really see it even at 1 year, or 28-day data, but we really see where the impacts are in long-term service life when we use slag cement and silica fume as a ternary blend. And here's the ionic diffusion coefficient as well. Again, just a little bit different way to look at this. And again, you're seeing very low when you're looking at the 1 year. So here a 4 and 40 blend. So I often, when I start looking at how I'm going to make my mixtures, especially for bridge design, in pavements, I'm looking for these longer-term solutions rather than just a quick fix. And then just kind of summarizing some things up here, I don't want to take too much time. We actually ran this corrosion service life of content versus time, and we can see that over the course of time, the critical threshold of black steel is here, but we can look at our duration and service life and see that obviously that my deck blend, 4% silica fume, 40% slag, where they kind of leveled out at. Very similar here at 6% silica fume and a 4 and 25 blend. So why silica fume can be expensive if we can reduce the amount of silica fume but supplement that with slag cement, it can be quite economical. And again, here we compared the Service Life 365 to the Stadium program. We see that there are a few differences here. So the Stadium is in the red and the Life 365. We do see that Life 365 treated a little bit nicer at times, which is good, but very similar at the 4 and 40 blend and also at the 40% slag blend. And again, we think some of it needs to look a little bit higher at the data. But certainly, the point I want to get across here is that what you put in is what you get out. And it has implications. So if I have materials and I'm using raw materials, there's all environmental factors, economic factors, and social indicators that come from the materials you use. And certainly it really has a big part to play in this whole idea of useful service life and how much maintenance and repair there is. And this comes back to your CO2 contents or your embodied energy. And certainly, you have to look at life cycle costing over time. So kind of in concluding, sustainability is really being recognized now. I don't know how many sustainable sessions I've seen this week, but it's been a lot. I've been doing this for 2 decades, so for me to see this is very exciting, but a lot of it is we're still not there yet. And we really need to utilize blended cements to maximize our durability and serviceability of structural concrete. So with that, I thank you for your time.